So I'm introducing Rohith Vulchi this afternoon. Rohit's got his bachelor's. Okay, need to make sure I say this right. Yep. Acharya N.G. Ranga, Agricultural University in India in 2016. He received his master's degree in entomology from California State University, Fresno in 2018, where he was also doing an internship on entomology research. He was looking to broaden his background, which is great going into industry because they're looking for additional knowledge around agronomy. So he decided to come into a weed science program where he's been at since coming into my program. And that was spring of 19.
All right. Thanks for the introduction, Dr. Nolte. Can everybody hear me well? All right. So my research is managing Palmer amaranth for long-term stewardship of XtendFlex Cotton in Texas. So I'll just give you a backstory before going into the presentation. Since 1994, Roundup Ready cotton varieties have been extensively adopted by cotton growers in the US, as well as Texas. It is mainly because the Roundup Ready or glyphosate-resistant cotton varieties produced greater yields, and also because of the use of glyphosate made it very easy for weed management. However, over a period of time, with heavy reliance on only glyphosate for weed management in cotton, it created herbicide-resistant problems in weeds. So here are a few graphs that I would like to show you that backs my statement. So the first graph tells us about the annual reports of glyphosate-resistant weed species in cotton since 2001. So what this basically tells us is there is at least one report of glyphosate-resistant weed species in the US every year, except for a few years where the data is missing. So I want you to focus on this color here, which is Amaranthus palmeri, the Palmer amaranth. You see at least one new report of glyphosate-resistant Palmer amaranth being reported in the US. So this graph tells us about herbicide-resistant weed species reported in the US since 2000, or from the beginning to 2021. So this graph here, oops. Okay. So this one here is Amaranthus palmeri, evolving resistant to different herbicides used in cotton since the beginning until 2021. So clearly, Amaranthus palmeri or Palmer amaranth is the most, devastating weed species in terms of evolving resistant to herbicide options in cotton. So just a breakdown of the previous graph to the number of herbicides Palmer amaranth evolved resistance to. It evolved resistance to different herbicides that are falling under 6 different modes of action. And we are running out of modes of action to control that weed or any other weed in cotton growing systems. So, which clearly makes it the most troublesome weed in cotton growing in the US. It also affects lint yields, lint quality, number of bolls per plant, and canopy volume at different densities in the field, basically reducing all those parameters that I talked about. It is also resistant to 6 different modes of action, and there are reports of multiple resistant Palmer amaranth reported in different cotton growing states. So let's talk about XtendFlex Cotton now. It is the first triple stack herbicide resistant cotton technology introduced in 2016-2017 growing season by Bayer. It allows post-emergence applications of dicamba, glufosinate, and glyphosate. It was introduced to manage tough to control glyphosate-resistant weeds, primarily glyphosate-resistant Palmer amaranth. By 2021, it was adopted in more than 60% of cotton growing acres in the US, as well as Texas. So from 2016-2017 through 2021, it almost was adopted in more than 60% within 4 years of introduction. So 60% of what? 60% of total cotton acres in the US is dicamba tolerant cotton. So from the lessons we learned with glyphosate or glyphosate resistant crops, reliance only on glyphosate or one single herbicide option is not sustainable. So we have high value traits like XtendFlex Cotton, which we want them to sustain longer. So we want to design herbicide programs or other weed management strategies in a way that these traits last longer into the future. So what are our options here? So herbicide programs, which includes residual herbicides, which sits in the ground and prevent germination of weeds and reduce the selection pressure on the post-emergence herbicides. Tillage options, conservation tillage practices like cover cropping and strip till can improve the soil quality and can increase yields of cotton during hard years or drought years. Conventional tillage can bury the small seeded broadleaf weeds like Palmer amaranth from the topsoil into the deeper layers of the soil, preventing it from germination. Another popular practice in Texas is crop rotation, rotating cotton with grain sorghum. So crop rotation provides two advantages. One, use of different chemistries in two different crops, one broadleaf and one grass species, reducing the probability of evolution of resistance to particular mode of action. Number two, it reduces the dominance of single weed species in a community, which fits very well to manage Palmer amaranth. So we believe integrated weed management strategies are necessary to protect the existing traits and post-emergence herbicide options. So for any new technology to succeed at the marketplace, one, it has to efficiently solve the problem the previous technology couldn't, and also it has to be an inexpensive alternative to the previous technology. So those two factors, if they go hand in hand, result in a successful market adoption of a technology. So that's what my research is all about. Managing Palmer amaranth under irrigated and dryland environments as influenced by combinations of tillage types, cropping sequences, and herbicide programs. Economics analysis piece, the one I listed here, stoplight chart analysis, is a portion of what I'm doing. It provides guidance to the risk-averse growers for adopting these weed control strategies. And the third objective is looking at the seed bank dynamics of Palmer amaranth as influenced by these treatment combinations. But for today, I'm going to just talk about the first two objectives here. Our hypothesis is crop rotation along with herbicide programs with residual herbicides may provide greater Palmer amaranth control in a longer run and consequently greater net returns, facilitating greater adoption by risk-averse growers. So this research has been conducted at 3 different locations in Texas, but I'm going to talk about the data from 2 locations: Extension Linear Farm, Snook, Texas, and the Stiles Farm in THRALL, Texas. The experimental design selected was a split plot design with 4 replications. The main plot are 3 different tillage types: no-till cover cropping, strip tillage, and conventional tillage. The split plot was cropping sequence, continuous cotton for 3 years, and the other cropping sequence was cotton during the first year, grain sorghum during the second year, and followed by cotton again during the 3rd year. The split plot was herbicide programs, 4 of them: a VD check, a weed-free check, low input herbicide program without any residual herbicides in it, and a high input herbicide program using residual herbicides in it. Cotton variety planted was Delta Pine 1646 Bolga 2 XtendFlex variety, and the grain sorghum variety planted was Decal 5707. So this is the graphical view of how the experimental design looks like. This is the research started in 2019 through 2021. During 2019, the ones in the green are no-till cover cropping system, which is the main plot. The one in the blue is strip tillage. One in the brown is the conventional tillage. During 2020, which is the 2nd year, half of each tillage type is rotated with sorghum. And the small squares in each cropping sequence is a herbicide program, which is replicated 4 times and randomized within the cropping sequence. And again, in 2020, all of them are planted back with cotton. So here's the list of herbicide programs used in the study, along with the VD check, which did not receive any herbicide treatments. The weed-free check contains pre-emergence herbicide application followed by 2 post applications. The low input herbicide program contains 2 post applications, and high input herbicide program contains 1 pre-emergence application followed by mid-post application followed by post-directed application. So here's the list of chemistries that were used in each herbicide program. The ones in the brown are cotton, the ones in the gray, blue are sorghum. So I want you to focus on weed-free check and high input herbicide program that are receiving residual herbicides being more expensive compared to the low input herbicide program that do not receive any herbicides. So our goal is to see if the low input herbicide programs, which is inexpensive compared to weed-free check and high input herbicide program, is enough to produce equal or greater net returns or equal or greater yields. That's the objective, along with good weed control. So the main plots, the cover crop varieties used were winter wheat varieties planted at 100 pounds per acre at College Station because it's a irrigated location, and at 65 pounds per acre at THRALL, which is a dryland location. Cover crops were chemically terminated 4 weeks prior to planting. In strip till plots, 1 strip till pass was carried out during early spring, and 2 diskings were carried out in conventional till plots, 1 a week after harvest of the previous crop and 1 during the spring. So the data collected were visual weed control ratings. Here I'm going to talk about Palmer Amaranth. 28 days after pre-emergence applications and 28 days after second post application. Cover crop biomass, Palmer Amaranth density before post-emergence applications, cotton yield and fiber quality parameters for economic analysis. The statistical analysis, prog limits in SAS was used for statistical analysis. Percent weed control data were subjected to ANOVA. Means were separated using 2 keys at alpha equal to 0.05. Graphs with different letters indicate they're significantly different at that alpha level. Years and replications are the random variables. Locations and treatments are the fixed variables. I got a very big 5-factor interaction. So I am presenting the data separately for each location and separately for year within each location. So fasten your seatbelts. So College Station, 28 days after pre-emergence timing. So during 2019 and 2022, you can see conventional till did very well in managing Palmer Amaranth. Even though statistically significant, numerically, strip till also gave consistent performance in managing Palmer Amaranth. However, you see a significant rise in the performance of no-till cover cropping systems from 2019 to 2020. This is because of the amount of cover crop biomass that was put out in 2020 by the cover cropping systems. That was a good year, greater than 4,000 kg per hectare rate of biomass was put out. So along with, averaging over herbicide programs, cover crop was able to provide equally good Palmer Amaranth control compared to conventional tillage. During 2021, which is the 3rd year, crop rotation, conventional till did just like the previous 2 years. However, in strip till and conventional till, crop rotation did very well in managing Palmer Amaranth compared to their counterparts in continuous cotton systems. So here's a picture in 2021, 28 days after pre-emergence timings in College Station. You can see the plots which were rotated with sorghum during the 2nd year were cleaner than the ones in the continuous cotton plots at the end of 3rd year between cover cropping system and conventional tillage. The second timing, 28 days after second post-application timing. So there are no significant difference between the herbicide programs. So averaging over herbicide programs and cropping sequences. All the three tillage types provided greater than 95% control. Those strip till is statistically significant from the other two tillage types. In 2022, again, conventional till provided greater palmer amaranth control. And strip till also over the two herbicide programs provided consistent control. In 2020, again, like I said before, because of high cover crop biomass that was put out during 2020, when it was tagged along with residual herbicides at pre-emergence timing and mid-post application, provided greater control compared to the low input herbicide program without any residual herbicides in it. Again, during 2020, conventional till provided, again, the greater palmer amaranth control. In case of cover cropping in 2021, so this is the year that we got frost. So there was not a lot of biomass that was put out by the cover crop. It was barely 600 kg per hectare rate, which is really not enough to manage palmer amaranth at 28 days after second post application timing. So overall, no-till cover cropping was not as good as the previous 2 years compared to conventional tillage. So here's a picture of comparing high input and low input herbicide programs in conventional tillage versus cover cropping system. This is all grass, not palmer amaranth. So there is a good control of palmer amaranth, but because of rainfall or other different factors, the grass control was poor during 2021. However, the palmer amaranth control was good. So second location, THRALL 28 days after pre-emergence application timing. So in all the 3 years, there is no significant difference between herbicide programs. It was only tillage level interaction that was observed. As you can see here, no-till cover cropping provided as much as 99% by the end of third year and 100% in conventional tillage, which means a no-till cover cropping can be a fitting alternative to conventional tillage cotton production systems in dryland conditions. So here's a picture comparing no-till cover crops, strip till and conventional till plots in 2021, 28 days after pre-emergence timing. Very clean. Second timing, 28 days after second post application timing. During 2019 and 2021, again, no significant differences were observed between no-till cover cropping and conventional till. Even strip till provided greater than 90% palmer amaranth control in both the years. They are just statistically different. Numerically, they're close, I would say. So that's during the first 2 years. And during the third year, there is no significant differences between the tillage types. The only difference observed was the interaction between cropping sequence and the herbicide program interaction. So if you can see in both low input herbicide program and high input herbicide program, crop rotation plots provided greater palmer amaranth management compared to the continuous cotton plots, except for continuous cotton plots that used low input herbicide programs. All of them provided, all the plots that got residual herbicides and rotated with sorghum provided greater palmer amaranth control. Here's a picture. See, the high input plots, regardless of continuous cotton or cotton sorghum rotation, were clean. And the ones in cotton sorghum rotation, even though it got low input, there are few escapes but still it's cleaner than the ones in the low input plots in continuous cotton system. So that's the weed control portion of it. Now let's see, let's look into the economics portion of this study. So the treatment costs included the herbicide chemical costs, the spray application costs, tillage costs, cotton and sorghum seed costs, trait technology costs. Location-specific individual field operation costs were estimated using the 2019 through 2021 custom rate surveys. The gross returns were calculated as the treatment yield times the seasonal based price adjusted for fiber quality premiums or discounts. So the partial net returns is calculated as gross return per acre minus chemical cost and treatment specific individual operational costs. The stoplight chart analysis that I'm going to present was conducted to graphically illustrate the net return distribution of these treatments. The lower and upper cutoff values were determined using the average net return of these treatments at the 25th percentile and the 75th percentile, following the procedure by Richardson 2010. So what it basically or simply means is, so this is the 25th percentile, less than $37 per acre. This is from the 25th percentile to 75th percentile. And this is greater than 75th percentile. So if a treatment, and in an x-axis, we have the treatments, and on y-axis is the probability for those treatments to provide net returns in these percentiles. If you look at this graph compares the herbicide programs in both irrigated and dryland environments. This graph talks about in the irrigated environment, you see the low input herbicide program provided greater than $429 per acre, shows a probability of 70%. Similarly, the low input herbicide program here do not have any red sign, stop sign. So 80% of the time it provided anywhere between $37 to $429, but there is a 20% chance that it can produce more than $429. When you compare this low input herbicide program with high input herbicide program, there is a slight chance of 10% that high input herbicide program can provide less than $37 per acre in irrigated conditions, and a little more than 10% in dryland environments. And there is a slight chance it can go more than 429%. The VD check, like we can assume, did not get any herbicide treatments, consequently lower yields and lower net returns. So this is the comparison between the herbicide programs. So this is for the cropping sequences, comparing continuous cotton for 3 years versus cotton followed by grain sorghum followed by cotton over 3 years. Like we can see, the crop rotation or the continuous cotton were, not really different in irrigated environments. However, in dryland environments, crop rotation proved to be very economical. Very less chance of producing less than 25th percentile and more compared to the continuous cotton systems. And there is slightly more than 10% of the times it can provide greater than $429, which is greater than 75th percentile. So overall, in dryland environments, crop rotation can be a profitable alternative to continuous cotton. However, in irrigated environments, the graphs are very close. Now, comparing tillage types. If you look at the irrigated environment, there is greater chance of, or more than 60% of the time, no-till cover cropping produce more than $429, which is the 75th percentile, compared to the conventional tillage, which basically says cover cropping can be a fitting alternative to the conventional till systems under irrigated conditions. When you look at the dryland conditions, conventional till, I don't know how many of you would like this, but conventional till proved to be economical compared to no-till systems, right? So, and no-till cover cropping almost at 40% of the time producing less than 25th percentile. This is based on the data that we generated over 3 years. However, if you produce more and more data, the models can change. It's just 3 years. So what it tells us is regarding the weed control part, using residual herbicides plus high biomass content in cover cropping can provide greater palmer amaranth control. When the cover crop biomass decreased below 600 kg per hectare during 2021, the palmer amaranth control was very poor. So if you can get a good cover crop biomass and tag it along with residual herbicides, chances are greater that it control palmer amaranth more efficiently. And looking at the dryland environment here, tillage level differences for palmer amaranth control were not identified, which means under dryland environments, no-till cover cropping can be a fitting alternative to conventional tillage. Using residual herbicides in dicamba-based herbicide programs provided greater palmer amaranth control throughout the 3 years. Crop rotation sequence provided greater than 95% palmer amaranth control at the end of 3rd year, even without residual herbicides. So in conclusion, crop rotations and residual herbicides provided consistent palmer amaranth control in long term. High biomass cover crops plus residual herbicides can be an alternative for conventional till systems. Here are my references. I would like to thank Dr. Scott Nolte, Dr. Josh McGinty at Corpus Christi for helping me with these field trials, and Dr. Muthu Bhagwathianan for providing advice on statistical analysis, Matt Matoka, our previous extension program specialist, Zachary Howard, White Stutzman, my friends and graduate students in our group for providing all their help. With that, I'll take any questions.
We have time for a question or two. Questions? Oh, here's a close one.
Did you include any fuel costs with your tillage?
Yes.
So, go ahead.
Go ahead.
So my question would be, for a farmer who has a budget, what would you recommend as far as all the applications that you provide?
For the herbicide applications?
For all the options that you listed, which one would you recommend?
So it depends on how much budget he has. So anyway, so at the tillage level, we did not observe any cost differences between conventional till or the cover cropping systems. That is because you would still need to plant the cover crops. You would still have to go apply that herbicide to burn down the cover crop, instead of the 2 diskings, you plant and burn down the cover crop here. And additionally, we have application costs for herbicides. And depending on what herbicide you use, again, it raises or decreases the cost you spend on the herbicides. So it depends what's his end goal is. If you want to be a no-till farmer, improve the soil quality or something like that, then no-till cover cropping systems is a better choice. But if he has really severe weed infestation, big weeds or any other thing, conventional till can be a good starting point. But again, soil degradation has been a bigger problem in recent times. So you have to manage based on what your problem is and what your end goal is.
One more question.
So between your treatment types, you saw that the high input obviously had the most consistent control over the long run, yet your low input was the most economically feasible. So if you had a local farmer that was asking for recommendations, which treatment type would you recommend?
That's a good question. So this is the data from 3 years. So the low input herbicide programs have 2 post applications of same herbicides in both cropping sequences, which means if you use more and more of same herbicide over time, and if you collect data from the field, I believe there is a more chance that the low input herbicide program breaks before the high input herbicide programs, right? Even though we see the low input herbicide programs here doing well over 3 years, it can be a good recommendation in a short term, but in a long term, it's always important to diversify your weed management strategies. So again, if you are on a budget, low input herbicide programs. If your long-term goal is weed management, sustainably producing greater yields, then probably high input herbicide programs would be my answer.
Thank our speaker.